Hello, Professor Eric Linder.
Thank you for having me.
Yeah, thank you very much for accepting our invitation for this Zoom seminar.
Thank you.
As you know, our center, like many other institutes around the world, because of this corona pandemic, we are running this online seminar and lectures rather actively nowadays. So it's great pleasure to have you here as one of the lecturers. And actually, the day after tomorrow, we're going to have another lecture series about cosmology, which will be given by Misao Sasaki. So I think your lecture seems to be well paired with Misao's lecture series about cosmology. And our center is also very much interested in building up a new group working on cosmology. So this is great opportunity. And beside today's lecture, perhaps next year, I would like to invite you to come to our center, since you were elected as a Benjamin Lee professorship several years ago. I don't remember exactly.
Yeah.
So you should come again and stimulate our cosmology teams.
I would enjoy that very much. Well, my past visits to APCTP have always been very productive, very interactive, and I look forward to being able to do that again.
Okay, thank you very much. I think it's time for you to start. Okay.
Did you want to introduce
Right. Thank you.
No, you should be a chair. Okay.
Okay, so we're very pleased to have Professor Eric Linder here. Well, in some sense, in spirit anyway. And he's going to tell us about all cosmology all of the time.
That's right. Doesn't leave much for anyone else to talk about. Yeah, so the title of the talk is really saying that we don't want to focus too narrowly on any one aspect and get so excited, so wrapped up in one specific quantity or one specific time, either recombination or the present or whatever, but that we really want to keep in mind the big picture as we go along. So if you go to a conference, either virtually or as we used to do in person, then you notice that there's really two parts to the audience. There's one part that is very intent on finding the best precision on the parameters within what they say is the standard model of cosmology. And then there's another part of the audience which is really seeking flaws, seeking tensions, seeking anomalies, and trying to overset the standard model of cosmology. And so to start off, I want to talk a little bit about, well, what do we really mean by the standard model of cosmology? And in particular, once any of the excitement of either of these camps gets into the news media, then often we will get headlines such as, the Big Bang Theory is disproven, or cosmologists have no idea what the universe is, or whatever. So I wanted to take a step back and look a little bit about the foundations, what we really have a great deal of confidence in, and what do we mean by the standard model of cosmology as a series of layers, things that we have a great deal of confidence in, and then elaborations to that, which are part of the model, and then further elaborations, which you may or may not call part of the standard model of cosmology. Okay, so what is the standard model of cosmology? So a lot depends on where you are comfortable in drawing the line in talking about cosmology or talking about the universe. So one avenue that you could go down, one way of viewing it, is that cosmology is strictly the global properties of the universe. So these are things, and again, you can go, very fundamental. You can say, is the universe one thing? Can you get from any one part of the universe to another part of the universe? So is it smoothly connected, or is it, for example, topologically distinct regions? And I've written this in a way which is accessible to students and people from a little bit outside cosmology. I'm not sure if we have any in the audience, but I do encourage questions as we go along. And so I've written the smoothly connected part, not in topological terms, but just, can we get from here to there, okay? And then also in time, because of course we talk about space-time, can we get from then to now? So again, you can think of this topologically. You can also think about this on a quantum level of, is space-time a continuous quantity, or is there a discrete aspect to it? Then once you have a smooth manifold, or just think of it as a smooth space-time, you then have to ask, well, I can get from here to there and then to now. How do I tell how far in some sense of the word far? So how do we measure basically the distances in either space and time? And we do this by putting a metric on the space. You can't always do that, but we think that for our universe, that's a very reasonable thing to do, to talk about a metric space. And there are different types of metric spaces, and I'm not going to go into the technicalities of Riemannian or anything like that. Again, I'll talk about it in student terms. How far is it from here to there? How far is it from then to now? So these are things that we think are really part of our standard cosmological model, and we usually don't talk about these at conferences. Maybe some conferences we do. But when someone says, we've overthrown the Big Bang, standard cosmology, they don't mean that we've discovered that space-time is discrete. They don't mean to say that there is, a part of the universe that you can't get to or anything like that. Now we get a little bit more specific, and we say, as we talk about the global properties of the universe, we're going to say that it is homogeneous and isotropic. And this is something where observations clearly play a large role. We can measure isotropy. We can either count different types of sources, such as radio galaxies or quasars, in different parts of the sky, and we can say there's roughly equal numbers in equal areas of the sky. Of course, the cosmic microwave background radiation is the most excellent way of measuring isotropy of the universe. So now we've narrowed in our cosmological model to homogeneous and isotropic, which has a very definite implication that this metric that we put on the space has to take the Robertson-Walker form. So now we're in very familiar territory, and most introductory cosmology courses would start off right there. They wouldn't talk about these other levels of it. And so you have the standard model of cosmology with a Robertson-Walker metric on your smooth space. The Robertson-Walker metric has two parts to it. It has a scaling factor, a time-dependent factor, the expansion factor A of t, and it has the possibility for spatial curvature. Spatial curvature is optional. Expansion isn't, because we really observe that. We see redshifts of objects. We see that the temperature of radiation evolves and so forth. So now, one group of people would say that is our standard model of cosmology, where we have a Robertson-Walker metric, we have some expansion factor A of t, we may not specify necessarily what it is. And that is something which, again, people don't stand up at conferences and tend to say, no, we're throwing away that standard model. Almost everybody is pretty happy with using that sort of a concept of a standard cosmological model. So now let's go a little bit deeper from these global properties of the universe, and now say, look more at that evolution, at the history of the universe. And so we care about what the universe used to be like, what it is now, and how did it get from one state to the other state. So we talk about cosmology as the history of the universe, often by saying it came from an early hot dense state. And except for in news media, people don't really, scientists don't tend to mean anything very specific by the Big Bang. Okay, they're certainly not talking about a physical explosion. They're not usually even talking about T=0. Okay, they were stopping the early hot dense state either at an inflationary epoch and saying we're not sure what happened before that, or at the Planck era and saying we're not sure what happened before that, or something like that. So again, when the media say Big Bang is disproven, they're not really meaning early hot dense state is disproven, because we have a lot of great evidence for that, from primordial nucleosynthesis to cosmic microwave background, and so on and so forth. So I'm going to leave ambiguous where we're going to start that early hot dense state, whether you want to start it at the Planck energy, you want to start it at an inflation epoch around 10 to the 15th GeV, whether you want to start it above a quark-hadron phase transition around 10 to the 3 GeV. To me, that's a detail, obviously an important detail, but it's not going to rule in or rule out a standard model of cosmology. The next thing that's very obvious when we observe the universe is that there's this immense matter-antimatter asymmetry. And I have absolutely zero to say about this, because I and the vast majority of cosmologists just really don't have a handle on how to go about explaining the way our universe does it. There are theories for how it could arise. We know of particular conditions that this has to satisfy, but we don't have a detailed theory saying, yes, this is how our universe generated this matter-antimatter asymmetry. And it's an immense mystery. And again, you don't hear about this very much at most cosmology conferences because we have so little to say. Hopefully, some of the early career people in this audience are going to make progress on this question. But again, I'm not going to talk about it because I have no ideas for that. So then we get to the radiation era, and there's a lot of very important things that happen there. You have the synthesis of the nuclei, the light nuclei. So you have obviously hydrogen nuclei, you have the protons existing there in the quark-hadron phase transition. And then you build up, you get helium, you have lithium, and isotopes of those and so forth. So that's a very important part, and that has been pretty well studied. There's a few tensions there, such as the lithium abundance. And again, that's an interesting area to go into and to talk about, but it's unlikely to completely rule out the standard model of cosmology. If you have an extra particle that does something to the lithium, if there's an unusual process in stars that does something to the lithium, if there's some inhomogeneous nuclear synthesis, it's not going to overthrow the entire standard model of cosmology. It's important science, but it's not what I mean when we talk about tensions in standard model of cosmology. The degrees of freedom, which tells us basically how fast the evolution goes, how the radiation energy density evolves. That's again a very active topic of conversation in particle physics as well as cosmology. The two are really tightly intertwined there. And this has to do with things like when the neutrinos decouple, as this very dense early state becomes more and more diffuse during the expansion, the neutrino interactions, they lower, they stop being quite as frequent, and they decouple. You have an epoch of electron-positron annihilation, dumping some extra entropy in there, and this all goes into that degrees of freedom G star. So again, there's a huge amount of particle physics that can go into that, but the details of G star, again, it's not going to overthrow the standard model of cosmology. There's also the CMB thermalization epoch. So this is an epoch at around redshift of around 10 to the 5th, 10 to the 6th. And again, you don't hear people talk about that quite as much. And the idea is that's where the black body state of the CMB is fixed, basically. And we've observed that wonderfully with the COBE satellite. It's very interesting to think that since the COBE satellite measurements, we really haven't improved on the black body nature of the CMB. There was an attempt in the late 2000s by an experiment called Arcade, balloon-borne experiment, which measured at very, very long wavelengths. And it found slight deviations from the black body. And nobody's quite sure what to do with that. Is it systematics? Is there some physics there? And it's never been repeated. So that's an area where, again, you can say, you know, maybe we should revisit this and maybe we should really check for spectral distortions in the black body and any processes that go on after the CMB thermalization. So you hear people talk about things like a Compton Y distortion, a chemical potential mu distortion. These are things where, again, we simply have not done, you know, everything that we could do to look for these spectral distortions. So looking to the future, this is something that I think is worthy of research and worthy of experiments to really push further on those. But again, yes, it will change the history of the universe, but it's not going to change the standard model concept of going from an early hot dense state to a radiation state, to a matter state, to a current cosmic acceleration. So it depends how far down in the details you want to go to determine how worried you are about the standard model. We then get to the matter era. Again, that's very obvious. We look around us and we see, yes, there's lots of matter, there's lots of non-relativistic things that aren't moving very fast around. And of course, a huge fraction of cosmology research is talking about the growth of large-scale structure. How did galaxies form, stars form, black holes, clusters of galaxies, planets, all of that. And then we have this very odd thing that the matter era has basically gone away and it's been overtaken by this cosmic acceleration epoch. And we give the name dark energy to basically whatever is causing the cosmic acceleration. We don't know. That's again, a very, very active topic of cosmology research. And of course, the name of this lecture series is Dark Energy in the Dark Age. So I'm sure you'll hear quite a few talks about dark energy. So again, this view of cosmology as the history of the universe, if you only look at the black text, I don't think anyone is going to overthrow that standard model. They will change whether the early hot dense state is understood from 10 to the 3 GeV down or 10 to the 15 GeV down. They may change what goes into the degrees of freedom G star and so forth. They'll certainly change what dark energy is, but the basic standard model as this history, I think, is in fairly firm footing. We can go even further down in detail, and we can say cosmology is about the stuff in the universe. So far I've been talking about the global space-time and the global history, but there's all that stuff in the universe, and we can get into the details of that. So there's the cosmic microwave background, which has a very rich array of structure. It has angular anisotropies. It has polarization of the photons, spectral distortions, as I mentioned already. It also probes the larger scale, the topology of the universe. It probes the expansion history. It probes the initial conditions of the universe. So for example, you can test, are the photon perturbations adiabatic perturbations, or the matter perturbations adiabatic perturbations? Is the initial state, what sort of vacuum structure, if you have inflation, gives you those perturbations? Is it a Bunch-Davies vacuum, for example? Is it a squeeze state, and so forth? And so the stuff in the universe is very informative about the global properties as well. We can also look at the stuff in the universe of the large-scale structure. And I mentioned before, you know, planets, stars, galaxies, clusters of galaxies, but you can think of it a little bit more generally as the density field of objects, the velocity field, how they're moving with respect to the expansion, and then how are they accelerating with respect to the smooth expansion, which you can call the gravity field, because of course the Einstein equivalence principle teaches us acceleration is gravity. And so there's a lot of research going on in each of these, and in particular combining these together. Let's drill down a little deeper and talk about cosmology as the stuff in the universe. So not just large-scale structure, but what exactly is the large-scale structure. What are the galaxy properties? How are galaxy clusters formed in a cosmic web as you have a flow of matter toward each other? What are the detailed properties of the various particles and fields, such as neutrinos, neutrino mass, gravitational waves? What's producing those? Are they as in general relativity, or there are extra degrees of freedom, and so forth? And then keep going down and down and down. There's the properties of the stuff in the stuff. And now you worry about not just, is there a galaxy, but you worry about the structure of the galaxy. Does the galaxy have a cuspy core? Do we understand the tidal streams as one galaxy passes by another and gets partially stripped of its gas and stars? How do stars work? What makes a supernova explode? What makes exactly a Cepheid pulse? And so now this is what people tend to mean when they say that there are these tensions. They're saying, I don't like the fact that there seems to be a cuspy core or a lack of cuspy cores. I don't like the fact that there seems to be a lack of satellite galaxies, and that this is going to change the standard model of cosmology. So that is a point of view, but what I've shown you here is that is many, many levels along the line of what is the standard model of cosmology. So if you change something there, yes, maybe it will go upstream and affect some of the larger properties, but we shouldn't say that we've overthrown the Big Bang or we've overthrown the standard model of cosmology. We've learned some interesting science, and we look for consistency, but we shouldn't think that all of the complicated physics that goes into these things, the hydrodynamics, magnetic fields, baryonic dissipation, stellar feedback, we shouldn't blame it all on cosmology when we don't understand each of those well enough. So in the rest of the talk, I'm going to concentrate more on the slightly higher levels, a bit on the stuff in the universe, and a bit on the history. Cosmology is the history in the universe. So before I go on, let me ask if there are any questions, because again, I do encourage questions along the way. And I guess I can't see hands raised, so I guess our moderator will, or just speak up if you have a question.
Eric?
Yes.
Basically, you could have, the stuff at the bottom, you could have just put in astrophysics, basically.
Right, so where people draw the line between cosmology and astrophysics is a personal choice. Right, there is no, on arXiv, there is no Cosmo PH, there's an Astro PH, and then even astroph.co includes extragalactic, but a lot of people put, tidal streams under .co as well. So I'm not going to try to draw the line.
I have a question.
Yes.
So initially, in the initial part, you mentioned the possibility of having topologically distinct parts of the universe, right?
Mm.
Is there any? Do you think there's going to be any way to, verify that hypothesis?
So there's certain levels of tests we can do, in particular with the microwave background. You can look for periodic universes where the topology is such that it wraps back on itself. And you can put limits from the cosmic microwave background that periodic length has to be, so many factors larger than our horizon length, basically. A few times larger than our horizon length. So within our light horizon, we are rather confident that the universe is smoothly connected, is topologically simple within that. Beyond our light horizon, there could be, strange things going on that we haven't come up with a way to access so far. Yeah, originally when I wrote that down, I was thinking more about the discreteness of space-time, but then I sort of enlarged it to talking about global topology as well. All right, let me go on and we can get more questions along the way. So once we start talking about properties of the stuff in the stuff, okay, then we realize that cosmologing is hard. And I don't know if this is a saying that, how worldwide this saying is, but there's a very popular culture saying in the US among the young generation, adulting is hard, okay? Being an adult, being on your own, and dealing with your career and dealing with your life and stuff, that this is hard. So I've made this cosmology is hard, because those little details about the properties of neutrinos, about how galaxies form, these really do affect how we learn about the more fundamental stuff, the higher level stuff, and also what we can learn about that. So I want to give two examples here, and you will see archive articles about these where people say, oh, we're going to test this, and maybe you even find articles that say, oh, there's some tension and these relations have been disproven. And so I just want to go into them in a little bit of detail to say it's not that easy to just, take some data that someone else, spent their time observing, and then you just take the very sort of, end result stuff and then test these relations. So the first one is the temperature of the microwave background. Does this scale basically as the, let me move this. There we go. Okay. Yeah, I have the pictures on top of my equation. Right. So does this scale with the redshift? Basically, it's 1 over the scale factor, the way you would expect from a adiabatic expansion. And again, this is not particularly cosmology oriented. If you take a black body here on Earth, and a cavity, and you expand the length of the cavity, then you will expect that the wavelengths of the modes in the cavity should scale with the length of the cavity. So suppose you go out and you measure the cosmic microwave background temperature at some redshift, not just locally, and you ask, does it follow this relation? So either you said, I've thrown out the standard model of cosmology, the universe is not adiabatically expanding, or there can be some astrophysical systematic. So for example, you measured the temperature by measuring basically molecular resonances. Usually you do it through rotational or vibrational states. And maybe there's another source of excitation that you haven't taken into account. And that throws off the temperature. So when you get to these very fundamental tests, you really have to make sure that your astrophysics is extraordinarily well understood before you go around throwing out the standard model of cosmology, which has so much support from other areas. Another very popular test is comparing the luminosity distance to the angular diameter distance. And there's this particular relationship where you have a factor of 1 plus the redshift squared in between them. And so people go out and they measure luminosity distance from supernova, for example, angular diameter distance from, for example, baryon acoustic oscillations, the pattern of the density in galaxies. And they compare them and they say, oh, I came up with a different exponent than 1 plus z squared. So again, you have to make sure that you understand the systematics in your different probes. Did the galaxy selection function, is it exactly what you thought? We already know that when we do large galaxy surveys, such as the Sloan Digital Sky Survey 3, that what we observe in the northern hemisphere isn't exactly what we see in the southern hemisphere. We don't think that the universe is hemispherically asymmetric. Rather, we think that the galaxies that we've selected in these regions are different, or even things like the density of stars, which affects, we don't observe very close to a bright star, for example, because it overwhelms our detectors. And so we sort of remove some of the data, and maybe we're not removing the same sort of data from the south and from the north, and you have to take into account these selection effects. So again, you have to really think of how well you understand your astrophysics. Or is it some new physics? Are you ready to throw away the standard model of cosmology? But this relation that's written here derives from 4 different assumptions, 4 different tests, if you like, of not just the standard model of cosmology, but in the sense that I talked about at the very beginning, really, the highest level of what the global structure of space-time is. We have to have a metric on the space. We have to have what's called geodesic completeness, which means you can get from here to there and back again. You have to make sure that the photons that you're observing are traveling on null geodesics. They're not interacting with anything along the way. that if you like, you can think of this as Liouville's theorem, that you have a conserved phase space density. And you need adiabatic expansion because that 1 plus z factor is coming from the fact that wavelengths are changing as you adiabatically expand things. There's many different effects, and only if you're adiabatically expanding things do all the effects enter as this 1 plus z. So the question is, if you didn't observe that relation, which are you willing to throw away? Are you willing to throw away one of those new physics explanations? Or are you willing to say, I better look a little bit more carefully at my galaxy selection function? So this is why cosmology is hard. So that's just to keep in the back of your mind for the rest of the talk that when you hear about a tension in something, that you shouldn't just immediately think, oh, okay, that's a real tension, I better adjust my cosmological model, but that you should keep in the back of your mind, you know, there are a lot of astrophysics that goes into that, and you know, let me think about new physics because it's just so fun to do, but before I throw away a standard model, let me wait a little bit. Okay, there we go. Okay, so how do we go about, if cosmology is so hard, how do we get anywhere? How do we ever test the model or learn about the contents or the history of the universe? So again, we need rigorous data where we've really pushed the systematic uncertainties down as far as possible. We want multiple probes. We don't want to rely on any one way of learning about the universe. We want to make sure that they're all giving consistent answers. And so that allows us to have these cross checks as well. We also want consistency in our cosmological model at all cosmic times. We can't just say, oh, well, we can explain today perfectly well with a cosmic void right around the Earth, and that's all we need, because we also have to care about, well, what influence does that cosmic void have when we observe the cosmic microwave background from 13.7 billion years ago, or galaxy formation to give us the structure today. So we can't concentrate only on the present. We can't concentrate only on the cosmic microwave background recombination, last scattering. We really have to pay attention to everything along the way. Ideally, we would check both the expansion history, distances in the universe, that A of t that we had back at the high level, and also the growth history. How did that structure, how did the stuff in the universe evolve over time? How did it form from a homogeneous universe into one with clusters of galaxy clustering and so forth? And we also have now this new window in terms of gravitational waves. So we can test things with photons, we can test things with gravitational waves. We're not quite at the point where we can test things with neutrinos, but you know, that's going to be something very exciting to do as well. So again, data is what we're going to rely on to test our theories, to test our models. Okay. So now let me get to a specific tension which you cannot go to a cosmology conference without hearing about. You cannot, I think, probably not for a single day, go on archive without seeing a paper about an H0 tension and so forth. So there was just a conference at the European Southern Observatory last week. Well, not at the observatory, sponsored by the observatory, it was online, where you had many, many, many people arguing over if there's a tension in H0, what's the who's at fault for this tension, and so forth. So it is certainly true that if you look at the data that as it exists in the literature, that there is a clear tension between the values of the Hubble constant today, H0, between different probes. If you use the cosmic microwave background, if you do local measurements such as a distance ladder, which may be calibrated off of Cepheid stars, a distance ladder that may be calculated off stellar evolution, the tip of the red giant branch, and so forth. So there is this clear tension. By some accounts, it amounts up to a 5 sigma tension. And again, everyone is running around trying to point fingers at someone and saying it's their fault, that you know, their model is wrong, their data is wrong, and so forth. So for this talk, I'm going to take the data at face value. Let's just say everything that is published about the data is correct, and ask, how would we have to change our standard model of cosmology, whichever level you want to talk about it at, in order to explain this tension, in order to explain the data at all times from all the different probes. So before we dive into this, mention some other puzzles that are there beyond simply saying that there's this tension, which is that the two methods of local measurement that are most precise, this calibration by Cepheids versus tip of the red giant branch, they differ from each other by more than 2 sigma. And so which one do we believe? So the tip of the red giant branch is about 2 sigma, 2.5 sigma off from the cosmic microwave background value. And then the Cepheid calibrated distance ladder is another 2 sigma off from that. And that gives you your sort of 4 to 5 sigma off from the cosmic microwave background. But someone's either got to be wrong or just underestimating their error bars along the way. So that's a puzzle that we do want to remember about. You'll also see a lot of people claiming that it's early versus late cosmology, that something happened between the early universe and the late universe to change things. And I think this is a misnomer. This is not the right emphasis, because baryon acoustic oscillations, which are between redshifts, well measured between redshifts of sort of 0.2 and 1.5 or so, we would tend to call those late universe. They're certainly not as early as redshift 1100 CMB. And we can use the baryon acoustic oscillations without the CMB at all. We can either marginalize over the sound horizon distance, what I've written here is the drag distance, or drag, or we can add primordial nucleosynthesis. Primordial nucleosynthesis certainly is early universe, but it's not the CMB. And it's something that we have a great deal of confidence in. So I think it's a little too naive to just talk about early versus late in this, because some of the late probes, late universe probes, really do give the same answer as the CMB and a very different answer from the local distance ladder. And then you've got the strong lensing time delays. This is a new probe. Again, this is what I talked about in the previous slides. We want new probes to come in. We want to cross-check and all that. And there's only 7 data points, basically 7 well-characterized strong lens systems. But if you look at them, then you see that the upper 5, the highest redshift 5 of them, are completely consistent with the microwave background result. And the lowest redshift 2 of them, are completely consistent with the local distance ladder Cepheid result. So what we can call the low H0 value and the high H0 value. So what's going on there? This is all late universe, okay? This is all redshifts of 0.3 to 1-ish. And yet, again, we seem to see this tension within this probe. So I'm going to take the data at face value, but again, keep in mind that there are these things that we're, there are more puzzles than simply saying one value of H0 from Cepheids and one value of H0 from the cosmic microwave background. Okay, so a little bit more detail. The cosmic microwave background data, if you fit it within the lambda CDM model, so that's cold dark matter model with a cosmological constant, then it gives a very precise answer of what we'll call the low H0, a value of about 67 kilometers per second per megaparsec. If you take the same data and you don't fit it within lambda CDM, if you say instead of the dark energy being a constant in density, that it's power law in density, that there's this equation of state W, which is different from -1, then the CMB data simply does not have the leverage to really constrain H0. It almost fills whatever priors you put on it. And so this really seems to be a lambda CDM sort of statement that you get this low H0 from the CMB data. However, when you add extra data in, other than the CMB, then you do get the leverage, you do get the power to probe in other cosmological models. And in particular, the cosmic microwave background, together with the baryon acoustic oscillation pattern in galaxy clustering, those give a low value of H0, even if you're outside the lambda CDM model. It is extremely difficult using those data, and in particular, also using other distance data such as supernovae. It is very hard to push H0, the Hubble constant, above 70. And so I show some figures here from a 2017 paper. So I know that Eleonora Di Valentino is going to give one of these lectures in a few weeks. So you'll get to hear a lot of detail from her. So in this paper, you can see different contours, and this is just shaded from green to blue. And what we're doing is we're just putting by hand a prior on H0. Okay, we're not using data, we're just putting an H0 prior on, and then combining that with the Planck data. And you see that as we move toward the gray, so the gray is H0 of 70, then your contour lies all the way to the left of the vertical. Can you see the cursor as I move it up and down? I couldn't actually hear an answer, but I'll assume the answer is yes.
Yeah, we can see it.
Okay, yeah, so as you push H0 higher, then you're moving that contour basically all the way to the left of the vertical line. And that's into a negative, W more negative than -1, what's called the phantom regime. And then in the two smaller panels, I've broken it up into what Planck plus supernovae, the JLA compilation, this was done back in 2017, and Planck plus the BAO at the time. And you can see they both lie to the right of that, that vertical dashed line. And so it's really very hard to fit the combined probes of CMB plus supernova, CMB plus BAO, or even better, CMB plus BAO plus supernovae, and get an H0 that is larger than 70. Very, very, very tough to do. So that's a challenge.
Sorry, Eric, can I ask you, are you worried about the assumptions that go into BAO? So BAO assumes a fiducial cosmology, which is typically lambda CDM. And of course, this could be affecting everything. I mean,
right. So
concerned are you about this?
There are people on this call who are far more expert than me on the actual data analysis of the BAO. I'm going to hold to my party line of saying I take all the data at face value. In other words, the way that they're interpreted is correct, and then ask, what are our ways out of this?
So just can I ask, you would trust, okay, but even between supernovae and BAO, do you have a preference for which you would trust more? Or are you just going to take everything?
I would like a cosmology model that fits all the data, or that we understand why some data need to be viewed in a different way.
Thanks.
Okay, so again, I'm going to take the premise that we're going to use all the data the way it's given, and we just saw it's really hard to push H0 greater than 70, and ask, okay, all these clever theorists out there, what are the ways out? Theorists can always find loopholes in anything. So what are the ways out of this argument that you can't get H0 greater than 70? So there's really two generic ways that you can do this. You can either do a late time transition, that is a transition in the recent universe at redshift less than 1, where you suddenly do something fairly drastic to the dark energy density. And again, we saw in the previous diagram that it has to push W below -1 into this phantom regime. Why does it have to be so sharp? Because if you make it be more gentle, like with a constant W that is less than -1, then you're going to change all the distances. So you want it to be sharp enough that the distances basically haven't noticed that you've changed the universe, because distances are an integral relation between you, all the conditions between you and whatever redshift you're measuring the object at. And so if it's sharp enough, then the distances haven't quite caught up to that change yet. So that's one possibility. Another possibility is an early time transition, where you change things in the CMB. So back at the recombination epoch. What you're doing there is you're lowering the sound horizon, and that makes the Hubble parameter go up. Again, that has to be a very sharp transition because you don't want to mess up the CMB. And so it has to be a sharp transition where you put a bunch of dark energy in, what we'll call early dark energy in, to lower the sound horizon. But then you have to very quickly get rid of that early dark energy, or it's going to mess up the beautiful agreement you have with the CMB. So in either case, you need these very sharp transitions. And so these are very different models than a WCDM model like that. And so these are the ways out that theorists have come up with.
So Eric, can I just make a point? So you mentioned basically this step in basically the holy cow data, right? So in the strongly lensed quasars. Do you understand how early time transitions would explain that?
They wouldn't. yeah. The strong lensing data is a definite. Yeah, it's as I say, it's one of the puzzles. Just along with why does tip of the red giant branch distance ladder not agree so well with Cepheid distance ladder? You need someone deep in the data to address that. Okay, so let me talk a little bit about early time transition. Most of the time I'll talk about late time transition. So we need this extra energy density. This is not something recently discovered. This degeneracy of how H0 will vary if you change the sound horizon dates back before Eustathiou and Bond 1998, but some of the common references are there. And then a little known but kind of interesting thing is in Korea at the Institute for the Early Universe at Eoin University during 2013, we actually discovered exactly the early time transition that you need for H0. At the time, there was no big H0 tension, so not a big deal was made about it. It did get into a physical review letter. And so here you see the diagram where you see this very sharp transition, so this either black or green curve, where the energy density delta is suddenly rising up and then suddenly falling back down right around recombination. And then in the inset, you see what that does to H0. So this is not a model. This is a model independent reconstruction from the best data we had at the time, the Planck 2013 data and the WMAP9 data. And we said the data says there is this transition and there is this shift in H0. Again, at the time, no one cared about H0, so it was not a big deal. But this was rediscovered recently in a series of papers that started in 2019 and has been talked about quite a lot.
Sorry, Eric, can I ask a question? Then is this because basically the Planck H0 value is lower than WMAP? Was that the point, basically, to explain this slight shift? I mean, what was the patient?
Yeah, at the time, the Planck data really, they had a lot of problem with the low L's, and so the WMAP9 data was really doing the low multiples in this combination. It wasn't a difference between the whole data sets as such. So again, I'm not going to talk more about the early time transitions. I just have this red comment, early transitions don't really work, and point to this paper here. Okay. Again, it's not an absolute statement. Theorists will always find a way around it, but I'm not very enthusiastic about early time transition. So let's move to late time transitions. So with a larger H0, we don't want to change the distances. And so that means that the Hubble parameter at higher redshifts has to be a bit smaller. That is, we need less energy density. So that means relative to the dark energy density today, we need less dark energy density in the past. So it has to suddenly appear. And that's exactly what a phantom dark energy model does. And that's why we need a phantom dark energy model to do these late time transitions. So there's three different approaches that you can take to this. There are phenomenological models, and again, Arman and collaborators on this call have done a lot of work on that. There's trying to start with a fundamental theory that has this sort of transition. And one that I have a soft spot for is called vacuum metamorphosis. This is a model from Leonard Parker from quite a long time ago, where he does a quantum gravity summation of loop corrections to all orders. And he does this very interesting heat kernel summation and comes up with a finite theory. And there's a series of papers here about that. And then there's this interesting, odd little theory, which here I call an emergent theory, from Khosravi et al., which they call uber gravity, which it's interesting because it's so different. And again, it gives you this late time transition. And these are the last two are generalizations of Starobinsky R-squared gravity. And of course, Starobinsky R-squared gravity is something which is which a lot of people take very seriously and work on. So I think to some extent you can argue that these theories are worth taking a look at as well. So with vacuum metamorphosis, one very naturally can get an H0 value, a Hubble constant value of 73. So you're not putting in any local distance data, you're not putting in any prior from Cepheids, you're not putting in any prior from typical red giant branch, you're just using CMB and BAO data, or CMB, BAO, and supernova data. And you come out with H0 of 73. You might say, does that explain the tension then? Should we take vacuum metamorphosis as, or some similar late time transition as, the extension to our standard model? You get a lower matter density out of this, which, doesn't tend to upset too many people. However, when you look at the structure, the growth of structure, and in particular how much clustering there is, it gives a high mass fluctuation amplitude, what's called sigma 8 of 0.88, whereas lambda CDM gets around 0.81, and there's a lot of people out there who actually like a smaller value down around 0.75, 0.77 from weak lensing data. And this is very common to any late time phase transition. You will almost always get a very high sigma 8 out of it. And I explain the reasons why here. So that can be a problem. But to some extent, most probes don't actually measure sigma 8. They derive it and they'll put it in their abstract. But what they actually measure is a quantity called S8, which is the combination between sigma 8 and the matter density omega matter. Since omega matter has been pushed low, then even a high sigma 8 comes down a little bit in S8. And you get a value of 0.83. In lambda CDM, you get a value of about 0.82, so that's pretty comparable. Again, there are people out there who would prefer a value down in the 0.78 range. Okay, so it looks like this vacuum metamorphosis or some sort of late time phase transition can get you this high H0 and maybe get you a structure parameter which is not crazy, at least not any crazier than lambda CDM is. So here is a diagram showing that. So I have expansion history on the y-axis and growth history on the x-axis. So S8 is a growth parameter. Here I've written it as F sigma 8, which may be more familiar to those of you who do redshift space distortions. But S8, at redshift 0, S8 is simply 1.94 times F sigma 8 at redshift 0. It's just a constant translation between them. So down by the cyan line, you can see what lambda CDM gives. It gives 67.3 or 0.6 or something. And it gives about 0.43 on F sigma 8. So vacuum metamorphosis models are up near the green line, which is the Cepheid Rees et al. 2019 value for the Hubble parameter at redshift 0. Okay? So these models are good, and we can see that this particular vacuum metamorphosis model is also good on the growth parameter, whereas this one had too high. No VEV for the particle physicists in the audience, they know that means no vacuum expectation value, which means it has no extra cosmological constant associated with it. Unfortunately, that simpler, more elegant model isn't the one that works as well as the one which does have a cosmological constant associated with it as well. So this is a paper that, again, Eleonora, who's going to be talking in a few weeks, and I and Alessandro Melchiori, it's submitted to archive already, so it should appear in the next mailing. And you can see that's what this, our particular late time transition called vacuum anamorphosis does. But there's this z=0 thing up here. So before we declare victory by saying, oh, well, we got the high H0 value and we're reasonable on the growth value, we have to remember what I had several slides earlier. We want all cosmology all the time. We want to fit all the probes, not just at z=0, but over the sweep of cosmic history. So now let me zoom out from this diagram and give you the full diagram. So the first, the one on the previous slide was this little orange box. It only showed the endpoints of these history curves. So this is what I call conjoined history, where I've got what the universe is doing in expansion history on the y-axis, what the universe is doing on growth history on the x-axis. And then you can see how one plays off against the other. So the black curve is lambda CDM, the best fit to the Planck plus BAO plus supernovae curve. The blue and the red curves are these vacuum metamorphosis models. And you can see that the blue curve, which is, that endpoint right there, when you look at the whole history, yes, it does great on H0 here and it does okay on the growth here. But then you can see as we look back through the history, it's doing this big excursion in growth. So any data that's consistent with lambda CDM on growth and distances is not going to be consistent with this vacuum metamorphosis model. So when you take into account all cosmic times and all probes, then the vacuum metamorphosis model does not work. We fit H0, we do okay on S8, but we do not fit cosmology. And so when you see theory papers saying, oh, we can push H0 up to this, look at the fine print. Do they actually fit all cosmology all the time? There's a paper which also says that late time transitions don't really work. They're looking at a pretty specific class of late time transitions, but some of their points are very interesting, so I encourage people to look at that. We saw early time transitions don't really work. So once you take into account all the data and all the times, then we're sort of stuck. And we're saying, we haven't managed to come up with a good cosmological model. We're fine with H0. We can fit H0 with no problem, but we can't fit H of Z. We can't fit all time. We can get a lower omega matter if we want, a lower matter density. We have problems with the amplitude of clustering, of structure formation, in particular as a function of redshift. We can sometimes make them work out at low redshift, but when you look at all redshifts, and remember the DESI experiment is going to be getting beautiful 1% measurements of that out to about redshift 1.5. The size of these error bars is 1% in F sigma 8 and in H. And so you see there's a big distance between what lambda CDM is saying and what vacuum metamorphosis is saying. This is redshift 0.6, redshift 1, redshift 1.5. So how do we solve this? You want to raise up H0, and we've seen to do that, we need to move into the phantom regime and lower the equation of state of dark energy. But that very generically raises sigma 8. In order to make everything work out, you have to raise the amount of clustering that there is. So how do we get sigma 8 back down? Well, maybe we can add in some extra neutrinos, more massive neutrinos than we might like. Maybe we can add in some interaction between dark matter and neutrinos, dark matter and dark energy, and that in turn is going to change this other stuff, which then we have to correct. So I start to wonder, are we dealing with epicycles here? As we try to make our cosmological model, we thought we could just change one thing, and it turns out, no, we have to change this other thing also. And that keeps leading us along this chain of things we have to change, these epicycles. And so at some point, you have to ask, is it really the model, or do I really want to take a much closer look at the systematics of all the different data sets. I'm not going to take a stand on that. There are people already looking at both categories. But I encourage everyone to keep both of them in mind as you worry about any of these sort of tensions. Is there a way? Okay, let me speed up a little bit. This is about gravitational waves, so I did want to throw this in. So this is a little bit of a change of pace. But again, if we had a new window, that would have completely different systematics. In particular, if we're not dealing with photons, then some of the selection function issues with how we choose galaxies or supernovae would be different, at least, if not necessarily gone away. So what if we do gravitational waves? It's going to be a long time until we can really get robust measurements of the Hubble constant with gravitational wave distances. But they are very good at probing what I'll call space-time friction. So you might be familiar with Hubble friction. This is something that slows down the growth of structure. So in Newtonian physics, if you have a little bit of extra density, it has more gravity, and so it gobbles up more matter. And you get an exponential runaway process. You get this Jeans instability. In cosmology, we don't have an exponential process. We have a power law growth. And that's because of the Hubble friction, that this gobbling up is happening in an expanding universe. And so it's hard to get the mass to all cluster together. So the space-time friction acts in a similar way. As the gravitational wave propagates along, the space-time friction is basically damping the amplitude of that gravitational wave. But the way we measure distances to gravitational wave sources is by measuring the amplitude that we get off of theory. So for example, we do the in-spiral of binary black holes within post-Newtonian order, and then we compare it to the amplitude we observe, and we measure the distance from that ratio. So if there's this extra space-time friction, that's going to change gravitational wave distances. And so the question we have is gravity the same at all cosmic time? If it's not the same, if there's this friction, this time-changing friction, then the distances being measured through gravitational waves will not be the same as the distances being measured through photons. Changing the gravity also changes the growth of structure. And so this gives us a cross-check that if we can see a difference in distances from gravitational wave standard sirens relative to electromagnetic sources such as supernovae, that predicts there should be some change in large-scale structure growth. Conversely, if we want to change the growth of galaxy clustering to fix our sigma 8 problem, it may, depending on your theory, give you a prediction for how the gravitational wave distances should change relative to the electromagnetic distances. So here's examples of these exact predictions within 3 different modified gravity theories. The blue curves show how the gravitational wave distances should deviate from the general relativity predictions, and the black curves show how F sigma 8 should deviate from the lambda CDM general relativity curve. And you can see that they basically have similar patterns. One determines the other. But the patterns between the theories look different. And so if we could actually measure these with precision, we could not only do a cross-check, but we could zero in on a particular theory. And so I've created this new statistic, which is called D sub G, which gives us, instead of conjoined expansion and growth history, it's conjoined gravitational wave distances and growth of matter structures. And so this statistic is 1 for general relativity. And so we expect the data to just fall along this horizontal line. Whereas in these 3 theories, it's not only different than 1, but it has very different shapes between the different theories. So if we get to the state where we can measure gravitational wave standard siren distances accurately, and we'll be able to measure growth, then we'll be able to do this very interesting cross-check to learn more about growth and learn more about the gravity theory. So let me sum up. What we mean by the standard cosmological model is many different layers to it. Okay? There's very strong support for the deepest foundations. You're very unlikely to find a legitimate articles saying we've ruled out the Big Bang Theory, we've ruled out the standard model of cosmology. You're going to learn lots of interesting things, but the foundations are pretty robust. Lambda CDM tends to work very well. There are a few tensions here and there, and it's just not clear where they should be addressed. Early time transitions, late time transitions just don't seem to work. You need the data. You need all the cosmological probes over the whole cosmic history, all cosmology all the time. That's a nice, memorable phrase to leave this seminar with. Theorists like writing papers. There's tens of times more papers on unusual theories on arXiv than addressing what are the systematics that are possible in the data. Maybe we want to even up that number a little bit.
Well, this is good for experimentalists as well. They get citations, right?
Yeah. And then again, gravitational waves is a new window, and we really look forward to being able to use that, and it can be very informative and very predictive. And I'm looking forward to the questions and comments that you have. Thank you.
Okay, so thank you, Eric, for a very interesting talk. Are there any questions online? Is everybody asleep?
Yeah.
So we have one question, yeah?
Yeah, so hi, Eric.
Hello.
So I wanted to ask if you go back to the slide 14 with this plot. Yes, I don't really understand what's the dashed line and solid line difference.
The dotted lines, like blue, solid blue dotted?
Yes.
Right, so that's in the article with Eleonora and Alessandro, but I didn't mention it here. The dotted lines allow curvature free, so they're not flat, whereas the solid lines are restricting to a flat universe. So you can see that adding curvature doesn't actually help resolve the situation.
Okay, thanks.
Other questions?
We appear to have one more question, maybe.
Hi, this is Hatadru. So, is this a quite a generic feature that all the modified gravity which pushes the H naught up also pushes the structure, the epsigmite or the sigmite? So it is a very general thing, or are there plenty of exceptions, or at least 1-2 exceptions?
So what I had specifically been referring to was not in modified gravity, but just if you change dark energy to be phantom, either at early times or at late times, then it tends to raise sigma 8 up. And the explanations are in these slides. I didn't necessarily say them, and they're in the paper that will be out the next mailing. Within modified gravity, a scalar tensor theory, scalars give attractive forces. And so they tend to increase the growth of structure, and they would also increase the clustering. There are ways to make modified gravity theories where you don't, where you have other effects such that you can suppress the growth of structure as well. So you can't say anything completely general about if modified gravity should always push you one direction or another. You do have to look at different theories.
Okay, thanks.
Okay.
Hi, can you hear me?
Yes, I can.
Yeah. First of all, I'd like to thank for giving this very interesting and also fundamental talk about cosmology.
It was a real pleasure.
Yeah. I'm not working on cosmology or particle physics. I'm condensed matter theorist, so I'm absolutely ignorant about this field. So as a beginner, I'd like to ask you one very stupid question. Once in a while,
It'll be incredibly fundamental, something that is very deep. So please do ask the question.
yeah, thank you. Once in a while, I was told that the concept of dark energy itself is not well grounded, and it might be just a fictitious concept. So based on you keep emphasizing data and data and data. So based on your expertise about data existing at the moment, this concept of dark energy, how well it is grounded?
As I predicted, this is a very fundamental question. The way I use the phrase dark energy, I mean it as anything that causes cosmic acceleration. So cosmic acceleration is, I think, very well grounded in the data. We can look at the distances, we can look at the effects on the growth, we can look at the effects on the microwave background photons, and we know, yes, there is real cosmic acceleration going on. Whether what we call dark energy is a physical energy density, that is something that we don't have a good foundation for. The analogy that I like to give when I give these talks to non-cosmologists is the solar system. That when in the 1700s people noticed this tension, this anomaly in the orbit of Uranus in the outer solar system, they were saying, does that mean Newton was wrong, that we have to change the theory? Or does that mean that there was some physical object, a new planet? And they went out, they made the observations, and they found there is Neptune. There is this new physical material object. In the 19th century, when the inner solar system didn't agree with the data, there was this tension in the precession of the perihelion of Mercury, the same exact question came up. Is it the theory? Do we have to throw away Newton? Or is it a material object? Is it a planet inside the order of Mercury? And there the answer turned out to be, oh, it's not a material object, it's a change in the structure of the theory. Which one dark energy will turn out to be, I can't say, but either one is a completely reasonable possibility.
Okay,
so thank you for the question.
But at least you are saying that this expansion or acceleration of expansion rate of universe itself is true by the
Right. That is very well founded on the data. You would have to really do some very intricate things, I think, to remove all the lines of evidence that point to an actual cosmic acceleration.
Clear. Thank you very much. Yeah.
Maybe Benjamin had a question. Benjamin?
Yeah, I think Songwook had a question before me, no?
Okay.
Thank you, Benjamin, for giving me a chance first. So thank you for your wonderful talk. And I think the new statistics DG might be quite interesting, but to actually use this parameter, then it seems like we need lots of the gravitational wave observation and also survey projects. So do you or some of your colleagues have some plan for actually measuring this parameter?
So there are a number of very large collaborations that are working with advanced gravitational wave detectors. Of course, LIGO, advanced LIGO is going forward, and they're talking about LIGO A+. There is CAGRA joining from Japan. There's Virgo in Europe. Hopefully the Indian Gravitational Wave Observatory will get going. And then from space, LISA is due to launch in the 2030s. So it's a little bit outside my time frame to wait for LISA to map these out to the redshift of 3 or 5. But some students in the audience, I think they may well be able to do this.
Thank you.
Yeah, so my question was actually related. So in your new statistic DG, so yeah, I'm trying to get some grasp on it. So I guess you would have to measure. So on top you have the luminosity distance from G wave and the luminosity distance that you can measure from like supernovae or something. Now on the bottom, how would you measure the bottom ratio, basically the modified gravity to GR F sigma 8?
Right. So the F sigma 8 modified gravity, that is your data. Okay.
Right.
When you calculate, well, what you're doing basically is you're calculating the ratio, you're doing the data, and the first question is it consistent with one at all redshifts? Is it just general relativity? The F sigma 8 general relativity is then a particular model. So you take lambda CDM with omega matter of 0.3 or something, and that's your prediction for it. So of course, changing your model is not going to change your gravitational wave luminosity distance. Well, it's not going to give you this extra space-time friction part of it. But yeah, the data, you will have this DG at many redshifts, again in this far future, and then you see, is it consistent with one? If not, is one of these curves or whatever your favorite theory is, is it closer to one of those than another? But you can see that to distinguish between the curves, we need a broad range in scale factor here or redshift. So it's not something we're going to do in the next few years, but it's at least a concept for how you could use the gravitational waves to cross-check your growth measurements and your distance measurement.
Nice, thanks.
Any more questions? Comments?
Can I ask a quick question, Owen?
Okay, yeah, Sudo.
Yeah, hi. So I don't know if you already considered this in one of the late time solutions, but did you look at this interacting dark matter, dark energy kind of models?
So I didn't personally. There certainly are papers in the literature about it, and I know that some of them say they can get high H naughts. I don't know if they've looked at consistency with all of the probes or not. I really haven't followed it closely enough.
Okay, thank you.
Yeah, I think that's true. Like if you look at some of Eleonora's work, she can get H074, but it's basically using Planck data, and it's using some weak lensing results, and they don't use BAO and they don't use supernovae. But once you put them in, 74 becomes 72, and then it becomes 70. So it's more or less consistent with what Eric was saying.
Okay.
That's a good point. Any tough question, I should just say, oh, Eleanor is going to answer that.
Exactly. Yeah, Eleanor's an expert, right? This is a warm up for Eleonora, right? The tough questions. Okay, good. Any more questions or comments? Okay, if not, well, we can thank Eric for a very interesting talk and for starting the series. It's been
this worked remarkably well doing it over Zoom. So thanks for setting it up.
Okay, thank you, Eric.
Okay.
Bye-bye.
Bye.